Start recording. Let's go to Chem 12. 8. Here we go. Huh? There was a water bottle and it smelled like what?
You said
like mold. Yes, I remember it smelled like mold.
It smelled amazing. It smelled amazing. She doesn't agree.
All right. Yeah, perfect. Okay. Kinetics. We need kinetics. Kinetics 8. There we are. Oh, hang on. Where did I put it? Well, let's go here then. Okay. Copy. Okay. Sorry, it's having a little hissy fit here. It's not responding. Okay. All righty. So we wanted 97.
I was just like 18 and then I swapped it.
97. Which of the following best describes the role of the spark plug in an automobile engine? Number 97. Oh, pen not working. Why pen not work? That's no good. Must be not charged. Okay. Let's grab this one. Does the spark decrease the energy of activation, the activation energy? No, that would be something that a catalyst does. A spark is not a catalyst because a catalyst is a chemical substance. Yes? A spark increases the concentration of the volatile reactant. That doesn't even make any sense, so I would say that one is probably wrong. The spark supplies some of the energy of activation for the combustion reaction. Is that possible? Well, let's think about that. It provides a more favorable activated complex for the combustion reaction. That would be something that a catalyst does. Spark is not a catalyst. It supplies some of the energy of activation. Yeah? Because what is a spark? It's energy. It's heat. Yeah? So it's going to make the particles move faster. Move faster. They have more kinetic energy. Therefore, a greater percent have enough energy to form an activated complex. Next.
$32.
32. Okay. 32, we have household bleach, NaClO, sodium hypochlorite, decomposes according to the following reaction. The rate of this reaction can be monitored by measuring a decrease in the concentration of chloride. Chloride, is that a reactant or a product? Product. Therefore, can we measure its decrease? Do products decrease in concentration over time? No.
Negative decrease, negative.
Nobody's going to say a negative decrease. No, no. You either say a decrease or you say that the change is negative. Okay, so you wouldn't say a negative decrease. Yeah. Can we measure an increase in the concentration of Na? We go from 2Na to 2Na. Oh, that's a spectator ion, so nope. An increase in the concentration of ClO. ClO is a reactant. Is it going to increase or decrease? It's going to decrease, so this would have to be wrong. And an increase in the volume of O2, we have made some O2, so yes, that will go up. Yes? Okay. Are people looking for questions or are we done? Because I'm happy to answer questions, but if we don't have any, I'm also happy to move on. Anyone looking for questions to ask? Okay, I'll give you another minute. Yes. 93. Okay, C2H4 is reduced by H2. You don't need to know what reduction is at this point. You can just say, okay, we have this reaction in the presence of a solid platinum catalyst, as represented by the equation above. Factors that could affect the rate of the reaction include which of the following? If we change the concentration of H2, would that affect the rate? Yes. Changes in the particle size of the platinum catalyst. Yes. I wouldn't ask this to you on our test because we haven't gone too much into the specifics of catalysts, but one way that catalysts act is by providing a surface on which the reaction can occur. No, the catalyst itself will be a solid. So it will provide a surface. So you've got two gases, but that platinum, whatever quality the platinum has, it'll be like, oh, hey, gases, you can hang out here and do your reacting. I don't know why it does that, but it does. So yes, and then changes in the temperature, will that change the rate? Yes. Okay, but like I said, I'm not going to ask you something like that where we're talking about properties of like different types of catalysts because we haven't really gone into that. Okay. So that would be E, 1, 2, and 3. Yeah. So for next time, make a list so you don't have to look through. Just on the front of your page, write them all out. Yeah, 93? We just did 93. Oh, concentration of a gas is the same as pressure of a gas, partial pressure of a gas. So like if I had two H2 particles, I could increase the concentration just by adding more to the volume. Yeah? Yeah. So gases can have concentration, aqueous has concentration, nothing else has concentration. Yeah, yeah. Questions going once? Questions going twice? Questions going 3 times? And equilibrium it is. Okay. All right. So last day you were actually asked to do this question. This is page 26 in your workbook. So I'll give you a minute to get that open. Steep and shallow. It's a way of remembering steep and shallow. Steep, shallow, flat. Steve, Charlotte, flat. No, it's okay. It was a suggestion after class as a little memory device. And so I wrote it down because I thought it was kind of cute. Steep, shallow, flat. Steep, shallow, flat. So the steep, shallow, flat refers to, if you remember, at the beginning of the curve, it is the steepest. Near the end of the curved part, it is the shallowest. And eventually it should be flat because we have reached equilibrium and the concentration remains constant. Okay, so are the slopes at the beginning steep or shallow? They are steep. I cannot write the letter S apparently, which is embarrassing seeing as my last name starts with it. This means that at the beginning of the shift, the concentrations, are they changing quickly or slowly? They are changing quickly. A steep slope means a fast rate of change. Towards the end of the shift, we just said those are shallow. The slope is shallow. That means that towards the end of the shift, the concentrations are changing slowly. Concentration is an example of what type of property? Macroscopic, yes. And we know that all macroscopic properties, including concentration, what is true about them at equilibrium? They are constant. Okay, very good. All right. Hopefully you remember from last week, although it's been a little while and you were probably studying reaction rates, we start usually with an old equilibrium where the two rates, this one is a rate diagram. So we have our rate there. And then we have a stress. Remember, stresses show up as vertical spikes. And then the shift is the smooth curve. And then the new equilibrium, the two rates are the same again. When we have a concentration diagram, are the concentrations equal to each other at equilibrium? No, they are just constant. So the concentrations are constant. And then we have a stress, which shows up as a vertical spike. And then we have our shift, which is a smooth curve. And then we have flat again, which is, of course, our new equilibrium. So those are the general features that you should see on each curve. And remember, the curve is always going to be steep, shallow, flat. Yes?
When you put stress onto the system, we're only stressing the forward rate.
No, it could be the reverse rate. You would add some product to the reaction vessel, or you could remove some product from the reaction vessel. When you change temperature, you're changing forward and reverse rates. Okay, so that would show up as a stress in the rate diagram, because both rates would change. Yeah.
Sorry.
Yes.
For the rate diagram,
Yep.
for the shift, we have two curves, right? The red one and the
Yep.
Which one is like the shift that we say is the response to the
Both of those are the shift. This
So is it increase?
is the shift, and this is the shift.
So was it this increase or decrease?
The shift brings us, well, the forward rate decreases, the reverse rate increases. They both end up at a higher level than before. So the rate ends up being faster than before because there's simply perhaps more particles in the system. Yeah? So you would start maybe with more reactant, let's say, right? And then you would end up with more reactant and more product, so everything would be faster. Yeah. So when a system is at equilibrium, the forward and reverse rates, I think we all know those are equal. Are the concentrations equal? No, what are they? They are constant, but not equal. What signifies a stress? Vertical spike, yes. What signifies a shift? Smooth curve, yeah. Now, most of the time, the change from stress to shift is sharp. Okay, it makes like a little point, but not 100% of the time, because occasionally you will get a stress that looks like this, and then the shift will go this way. And then that does not look like a sharp. So rather than saying that the stress to shift is sharp, what I want to say is that we should never have an S curve. Okay, this is an S curve. It looks like a reverse S in this case, but what that would be is if you have an S, it says that it is shallow, steep, shallow, flat. That means that the rate changes slowly, and then the concentration changes slowly, and then it speeds up, and then it slows down again, and then it remains constant. Is that what happens? No, the rate of change should be fastest at first. So this bit here is wrong. Okay, so anytime you see an S curve, and it's really tempting to draw them, I don't know why, but people want to. These are all wrong, 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 wrong. Okay, no S curves. Steep, shallow, flat. Same thing on a rate diagram. Wrong, wrong, wrong. S curve. Shallow, steep, shallow, no. Okay, it should just go steep, shallow, flat. Wrong, wrong. There we go. All right. So keep that in mind when you are drawing these diagrams. Other things that you could do wrong when you are drawing the diagrams. The new equilibrium has to be flat. Flat, flat, flat. Do you guys know what those little ditto marks mean? It means I'm repeating myself. Flat, flat, flat. This is a problem if you don't use a ruler or if you don't have good sketching skills. If you have good sketching skills, feel free to freehand it. If you do not have good sketching skills, use a ruler. Okay, because this is wrong. It doesn't go flat and then go down. It doesn't go flat and then go up. Okay, it doesn't go like that's wrong too, because it does not continue to go up. Yes. Oh, good. Okay. At equilibrium, the macroscopic observable properties are constants, and this includes the concentration. What are some other macroscopic properties? Tell your partner.
Just pick up the remaining three.
A catalyst is a factor that can change a rate, but it's not a property. A property is something that you could measure or observe. Yeah? Yeah. All right. Anyone want to give me a macroscopic property? Yes. Pressure. What else have we got? Yes. Color. Yes.
Temperature?
Temperature. Yes. Volume. Yes. pH. Mass. That's a pretty good list. Trying to think if we've missed anything. Not really. I mean, that's there might be other things, but those are kind of the important ones. Yeah. Okay. And that's it for 2.2a. So now we're going to focus in on the particular stress of concentration on page 29. So let's remember that stresses make the rates unequal. But shifts make the rates equal once again. Stresses are what we do to the system. Why do we want to stress the system? Because it's interesting. We might want to shift the reaction one direction or another in order to, say, make more product. Like if we had something that was reactant favored, we might want to do things to shift it toward the product. If it was something we were producing like to get out to market, you know what I mean? Yeah. Shifts is what the system does in response to the stress.
Not the stress. Do you have microscopic stress?
Stresses aren't considered microscopic or macroscopic. They're just like stresses.
Or like stresses are also macroscopic properties.
Some of them.
Oh,
I don't know. I think they just go in different bins in my head. So yes, they overlap, but not because they're properties, just because they happen to be the same things.
Can we say like a stress is a process and
A stress is a process. It is what we do. Yes, it is an action. A stress is basically an action that we do. A shift is an action that the system does. Yeah, no problem. That was a good question. I like that. All right, so we are now going to look at the system where we have H2 plus I2 in equilibrium with 2HI. If the system is at equilibrium, what can we say about the rates of forward and reverse reactions? They are equal. So if we were to draw this, our rate goes on the y-axis, our time goes on the x-axis. We have our forward rate and we have our reverse rate. And so we would draw them. Yes? You can use different colors, or if you just want to use pencil, you can use a dashed line for one of them. I want them to be distinct from one another, because if you do like this, do you know what I mean? Like, different colors is fine, but you can just use a dashed line or something like that to make it, then you don't have to be calling out different things, okay? I'll tend to do different colors just because it makes it more visual for you guys, but feel free to do it however is easiest for you. All right, and now what we are going to do is we are going to stress the system. So our stress is an increase in the concentration of H2. And if the stress is an increase in the concentration of H2, what happens to the forward rate? I'm going to rewrite this, H2 plus I2 to HI. Tell your partner, what happens to our forward rate when we increase concentration of H2? When we increase concentration of H2. And if you figured out what it does, explain to your partner why it does that. Perhaps thinking about tomorrow's test. What happens to our forward rate? Does it increase, decrease, or stay the same? You get to vote. Either increase, decrease, or stay the same. Yes, it increases. Can anyone tell me why? Pardon me? Higher concentration. Therefore, we have an increase in frequency of what? Yeah, frequency of collisions between reactant particles. By the way, BW, between. What happens to our reverse rate? Does it increase, decrease, or stay the same? When we inject that H2, what happens to it? Just in that moment. In that moment, does it increase, does it decrease, or does it stay the same? Up, down, stay the same? Oh, H2, thank you. Sorry, if you wrote this down,
Yeah.
I wrote HI, it should be H2. Okay, I'm gonna highlight that in green, my boo-boo. Okay, boo-boo has been fixed. Thank you. Let's vote. Reverse rate, increases, decreases, stays the same? I don't know yet. 5, 4, 3, 2, vote. It's okay to say, I don't know yet. In the moment. So in that moment, when we have added extra H2, have we done anything to the concentration of HI? No, we have not yet. There's no extra HI yet. And therefore, that rate stays the same. Reverse rate stays the same. So what's going to happen is, yes.
Like all properties are met. Is it everything reaches equilibrium?
As long as you've got a closed system and constant temperature, yes.
Everything.
Yes. Unless you've got a non-reversible reaction, in which case it just goes to completion.
So why would it be non-reversible?
Because it is much more thermodynamically favorable to go in the forward direction. It means it's both going to a lower enthalpy state, so it's going towards lower potential energy, but also it's becoming more random. We'll talk about this later, but the two forces that push a reaction in one direction or another are, is it going to a lower potential energy? That's one of them. But also, is it becoming messier, essentially? Okay, not really messier, it's more random. Okay, and again, that's a grade 12 explanation. If you go on to university, you'll learn about microstates and stuff, but we'll just say more random for now, okay? And as you can see, what does my desk spontaneously do? It becomes more random. And it requires effort to put it back, but spontaneously, it will just go towards extra randomness, okay? So here's our forward. Here's our reverse. And on our y-axis, what goes on the y-axis? Rate. What goes on the x-axis? Time. I almost wrote rat. The forward rate goes up at this time when we add H2. And the reverse rate does nothing. And now we're going to ask which reaction is favored. What favored means, it means to go faster or occur more. Yes, forward. Forward reaction is faster than reverse. I'm underlining than reverse because the forward reaction, the important part is that the forward reaction is faster than the reverse reaction, not that the forward reaction is faster than it was before. Because you can have a situation where the forward reaction is faster than it was before, but it is actually slower than the reverse reaction. We'll look at that later, okay? So it's important to say the forward is faster than the reverse.
Oh.
By the way, do you guys all know how I feel about skipping tests? Yeah, it's not a good thing. Okay. I will notice, I will keep track. If you have, like, I don't know, there's some people who always seem to be getting their passport renewed when it is test day, or their grandparent is in like hospital on test day, or like there's a lot of things. So you know what? If you are with your ailing grandparent in the hospital, I would like you to take a picture of yourself with your ailing grandparent in the hospital, just to be like, here I was. Yes, it was an emergency. I know these things do happen. They do happen, but they don't happen as often as people say they do. So if you had to go to the passport office, I want you to like take a picture of yourself at the passport office with the passport person, and then have them sign a piece of paper just saying, yes, today was the only day they could have done this. Okay? Right? Because otherwise it's just nonsense. Yes? So don't skip the test. Well, you're not going to have your new passport the day after you go and apply for it. So I don't think that matters. Yeah. Okay? If you're sick, but you're only sick on test days, I will notice that. Does it happen? Yes, it does. But I will notice. And I have powers that you all don't know about. You don't want to mess with me. Okay? Because although I can be a lovely person to lovely people, if you are not a lovely person, I am just waiting to press the smite button. Yes? Do you guys know what smite means? It's something that gods do, right? When their people have been misbehaving, they get a lightning bolt and they throw it at them. Smite. So if you have been misbehaving, I am happy to press the smite button. If you are having, mental health issues or something, and you would like to talk to me about them, I can be very, very, very understanding. Okay? But you need to talk to me like ahead of time, right? You don't have to share lots of details or whatever, but lots of reasons why you might miss a test, not lots of reasons why most people would miss a test, or people would miss many tests, more than one, say. Yes? You're going to be sick tomorrow. Okay, thank you for letting me know, Delcine. Okay, just so we're clear, I can be very understanding and very nice. I can also be like the avenging. What if you just overslept for period 3? Or period 4?
It's possible.
I slept in until 1:41, 2 o'clock. 2 o'clock. Okay, yes. Okay. Now, as a result of the forward rate, pen has stopped working. Let's try the other pen. Having issues with my pens today. As a result of the forward, I forgot to have this talk with my block 2. So if you know any of them, you can let them know. I will send out an email to them, but as a result of the forward rate being faster than the reverse rate, the system is now shifting, because if the two rates are unequal, it is shifting. As it shifts, what is going to happen to the concentrations? And remember, this is our reaction. H2 plus I2 to HI. What happens to our concentration of H2? The forward rate is faster than the reverse rate. What happens to the concentration of H2? Decreases, because it's being used faster than it's being produced. What happens to the concentration of I2? Decreases. It's being used faster than it is being produced. What happens to the concentration of HI? It increases because it is being produced faster than it is being used. As a result of my reactant concentrations decreasing and my product concentration increasing, what is going to happen to the forward rate? Forward rate will decrease. And what happens to the reverse rate? The reverse rate will increase. And you can think about why. Well, we draw the first part of the graph. We got rate here, we got time, we got forward, we got reverse.
And it's like, you did something to the over rate, right? Yeah, that's okay. Yeah. I just also explained. Yeah.
Our forward rate increased. Why does our forward rate now decrease? The concentration of reactants is decreasing. And therefore, lower frequency of collision. If you say less collision, that's fine too. Frequency? Frequency. Why does the reverse rate increase? Concentration of the products is increasing. Therefore, more collisions. And what should those graphs do? How should we show the forward rate decreasing and the reverse rate increasing? What shape should it take? Steep, shallow, flat. And remember, yes? It doesn't go, no. Okay. Okay, there we go. So that is the rate diagram for what happened there. Now let's draw a concentration diagram for the same scenario. When you are drawing a concentration diagram, you will need to be given the original equilibrium concentrations. Since we are mainly concerned with the stress and the shift, the initial concentrations are usually just set at some arbitrary value so we can see them going up and down from there. Okay, it doesn't really matter where we set them. This is a very qualitative thing. So we have H2I2 and 2HI. So I often will just, all other things being equal, I'll be like, okay, let's just do them in order. H2I2, HI. But it won't matter if we put them in a different order. That would be okay. Different order? Fine. This is a concentration graph. What goes on the y-axis? Concentration. Shocking. What's the unit? Molar. What goes on the y-axis? Time. And at time t, what did we do? We added H2, or you could say we increased the concentration of H2. Either of those would be fine. What would that look like on our graph? We're going to get a jump in all of them, in one of them, in some of them. In one of them, which one? H2. And now, let me write our equation again so you can see it. Whoops. What will happen to the concentration of H2? Is it going to increase, decrease, or stay the same? Now remember, what happened to our rate? Our forward rate increased and our reverse rate stayed the same. So what's going to happen to our concentration of H2? It's going to decrease because we're using it up faster. So it's going to decrease in what shape? Steep, shallow, flat. Okay, where does it end? Close to the initial, but not at or past. So steep, shallow, flat. And I'm not very good at drawing flat, so I'm going to try drawing it this way. There we go. Steep, shallow, flat. Yay. What happens to the concentration of I2? Again, we're using it up faster than we are producing it, so it is also going to go down. It's going to decrease by how much? The same amount, because this is a 1-to-1 ratio here. So this is going to go down. Try and make it look the same. Try and make it flatten out at the same time, if you can. I'm never very good at that. I'm going to be fairly generous with that. But remember, you can say, even if I did a terrible job making these the same, I can say that that distance is x and that distance is x.
Is it fine if we also write flat under
Yeah, if you're like, if I didn't draw it flat, you can be like, this is flat. Yes. Okay, labeling will fix all your problems. What happens to the concentration of HI? It's going to increase. By how much? Twice as much. Hang on. I don't want it to end sooner, so. There we go. Huh? They can cross, they can not cross. It just depends. If I had drawn my X value a lot smaller, they wouldn't cross. Do you know what I mean? Yes, Jonah. You can make it not cross. It's fine. You could, like, if I had wanted to, I could have been like, okay, this is this much, this is this much, this went down by here, this one went down by here, and then this one went up by 2x. Yeah? What? Oh, so let's say you did, let me draw a blue line. Say you did this. Yes? Oh, then that's less than x. And that's like you cannot fix all things with labels. Okay, if you make your 2x smaller than x, I think that's crossing some kind of line. And you could have just crossed this line instead. Okay? So the system has shifted. Which direction? It has shifted towards the products, which means that it has shifted to the right. How do we figure out that that's what happened? When it has shifted right, that means that we have ended up with more product than before. So When the forward reaction is faster than the reverse reaction, the system is shifting right.
Oh.
Okay? When forward rate is greater than reverse rate, the system is shifting right.
Question number 3, you said it's like the forward reactions favor.
Yep.
Oh.
Yes. And obviously then the reverse would also be true. When the forward rate is less than the reverse rate, the system would be shifting left. Okay. So when the stress was an increase in H2, the system shifted to the right. And you can figure that out by doing all of this rate stuff. Yes. And being like, oh, the forward rate is faster than the reverse rate, blah, 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 blah. But I'm going to show you a little trick right now, and you might not like it right in this moment, but you will like it eventually. Okay? If you say, I increased H2, okay? And if I were to make, this is like a little visualization thing, okay? If I were to make a little pulley system, there's a pulley, there's a pulley, okay? And now I've got my, now in order for H2 to go up, that means I would need to have pulled the rope this way, yes? Which would mean that the rope on top is going which direction? It's going to the right, which means that when I increase H2, the system shifts to the right. This is a quick way of figuring out which direction the system shifts. Don't worry, we'll go over this more as time goes on, okay? So another way to say it is that a system always shifts away from an increase in concentration. It will always shift towards a decrease in concentration, but I like the little visual, and I found that enough people like the visual that I still bother teaching it, even though some people hate it straight off the bat. So I will continue to teach it, but you can decide whether you like it or not. Are there any other concentration changes that we could have made to get the system to shift to the right? What could we have done? We could increase the concentration of I2. All right. What I want you to do now is I would like you to draw the rate diagram for that and the concentration diagram for that. Just to practice. This one should be pretty straightforward.
So the issue between like the concentration of the first should be as the same as what the
No, no. I could put them anywhere I wanted. I could make, did you guys have you done your concentration diagram yet? Yeah? No? You know what? For fun, let's put HI up here. Why not? Let's put I2 here. And let's put H2 here. What the heck? I can put them anywhere I want to. Unless I'm actually given concentrations, the initial concentrations are arbitrary. Unless you're given them. Okay? If you're given them, then you put them where they should be. Otherwise, it does not matter. You get to choose. Uh-oh. I don't know if you guys can tell why I say uh-oh. I haven't graphed this well. It's all right. Sometimes arbitrary doesn't work out well. I'm gonna make this small. Andy, you have a question? What is what? This word? Arbitrary, which means chosen just however you want, chosen at random. So it doesn't matter. Yeah. So if you're told the concentrations are something, that's great. If not, doesn't really matter. I just don't want you to get the idea that it's always like reactant product. Do you know what I mean? Yeah. I tend to do that because it's easiest. It's organized, but whatever. Check your diagram. Make sure that you've got steep, shallow, flat. Check that I2 went up in a spike. Check that I2 and H2 went down by 1x and HI went up by 2x. Make sure that I2 did not drop down below or to its original level. Okay? Because that's how I'll be marking it, right? Like I'll be like, oh no, I2 went below its original level, or it went to its original level. Yeah, so I would say you would want to label that here. Yeah? So this one was a bit of a gimme because it was very, very similar to the last one. I would like to know, is there any other way we can get this system to shift to the right? Yes? We can decrease HI, which is what you said as well. Temperature, do we know anything about where the heat term is in this equation? No, so we can't predict that at this point, but we know for sure that if we decrease the concentration of HI, yes, yeah, no problem. So this is our original equilibrium. I'm going to say our original equilibrium is like this. And there's a reason I made those arrows so big. If we decrease the concentration of HI, what happens to our forward rate? No change to forward rate. Oh, to HI. What happens to our reverse rate? It decreases, which is why I drew that so long, because now I can make this one smaller without like having to be like I don't want to do that. That's crazy. Okay. The reverse rate decreases. But it still means that the forward rate is faster than the reverse rate. If the forward rate is faster than the reverse rate, which way will the equilibrium shift? It will shift to the right. System will shift right. See if you can draw the rate diagram and the concentration diagram for this one. I think I'm going to go back to H2 and I2 and HI. H2, I2, HI.
Should they meet at this point for us to find it's like
Somewhere else is fine. Yeah. Are we okay with why the reverse rate decreased? I know my people who are like, got 100% in Chem 11 are telling me yes, but what about the people who got like maybe 86% in Chem 11 or something like that? Do you guys feel okay about like why the reverse rate decreased? There's less collisions because we have less HI. Yeah, okay. Good. If there's ever a situation where I say something like that and you're like, hang on, why? What should you do? You should be like, hang on, why? Because remember, who are you? You're my clientele, yes? And if you go to the hairdresser and you say, I want 1 inch taken off and they start taking off 2 inches, what should you do? You should be like, stop. Do not do that. I said 1 inch. Otherwise, you end up with your hair up to here. I don't know, and has anyone ever had that experience at the hairdresser? They understand their 1 inch is like this much. This is 1 inch to a hairdresser. I don't know why, but anyway, it is. But make sure you stand up for your rights and get the information that you need. Okay? Yeah, that would be like 2 inches for a hairdresser right there. Yeah, because that's what they do. And if you find one that doesn't, then you stay with them. Yes. Okay. Or you start cutting your own hair like I did, because too cheap and too lazy. All right. Are we good with the first diagram? The reverse will then come back up and the forward will go down and they will meet in the middle. And both rates are slower than before. Because we have less particles in total than we did before. For our second graph, HI should go down, and then it's going to go up. Does it make it to where it started? No, it stops before you get there. And that's going to be 2x. What do H2 and I2 do? They decrease by x. And those don't look anything alike, so I'm going to label them x so that we know that even though H2 looks like 1.5x, it's really supposed to be x. Is good? Okay, fantastic. Yes. You could do a half x. You could be like half x, 1x. That would also be fine. Yeah. What's that? Yeah, if you want to. Okay. And that is it for today. You guys have no homework other than to study for your test. And not sleep in till 2 o'clock. And not be going to the DMV to take your driver's license test without telling me first. No. If it's likely that you would do that, then you phone a friend and tell them to phone you. Yes.
So in your answer key,
Yes.
you drew this one a bit higher, like it was less. Like,
Uh-huh.
I'm gonna show you the answer key. Because it just looked right to me when it did.
Okay. It's highly exothermic, which probably means there's a bigger delta H. Yeah? I think that the term highly exothermic tells you there's a bigger delta H.
Okay.
Yeah? Yeah. Hi.
Hello, this is Theo.
Okay. Yes. Let me grab his quiz, which is here. I'll put it like that, and then you can flip that down. Okay. Yeah. And then there's a back. Okay, and then the same thing on the back. Oh no, he got it perfect. So
Hi.
good. Thank you.
See you tomorrow.
Yeah, see you tomorrow.
Okay.
Hi.
For this question,
Yeah.
I was wondering, the thing that determines the gravity
Uh-huh.
is the amount of molecules. So it's just
If you have positive and negative, they will attract one another. So if it's a double replacement or a neutralization, the positive and negative attracting each other will make it go faster. Yeah. Whereas this one, it has ions, but they're all kind of random and different
but
charges.
it wouldn't matter if it was like a solid with solid.
Solid with solid is like you wouldn't have ions that are solid with solid because they're already together, right? Because that's your solid. already together. There would be no ions in solid light. No separate ions.
There wouldn't be any double replacement.
No, not possible. They have to be aqueous.
Okay.
Yeah.
The molecule inside matter.
Not really, no.
Because I remember you said something.
No. I wouldn't worry about it.
Okay.
No.
So it's always going to be double replacement
Uh-huh.
or single replacement being.
No, not
Nothing.
single replacement,
But
double
double
replacement or
replacement.
neutralization, because neutralization is just a special
Because
double
they're pulling
replacement.
each other
Because the
together.
H and the OH are pulling together, yes.
Yeah.
Yeah,
Because they're made.
yeah,
Kind
yeah.
of like.
Yeah.
Hello.
Yes, it is. We're looking at science 10 right now. Yes. And we're doing chemistry at like an absolute
Yes.
and I've got a few kids who are probably taking English history next year. And
Yes.
just bored out of it.
Okay.
So like, you give them summer assignments. Do you have anything that would be like easy for me to send me that I could just print out for you? So if you're bored, I can be like, you can try this. You find this useful if you get into enriched chemistry.
I'll figure out something.
But
Yeah.
don't spend a lot of time on it, but just
No.
make it easy.
But I'll just figure out what, yeah. Cool.
Because it'll take 5 minutes for like taking it off.
Yeah.
Be like, look at this.
Because the catalyst works for both, right?
No, unless you sell it, that's a reversible, that's like.
Yeah.
Yeah. Well, then like, you didn't buy mostly. Just
No.
like.
Related in both, right?
Yeah, that's how I feel with my, that's how I feel with my. I don't have my name. My.
Oh man, wow.
Yeah. I've seen that is.
Why? Big thing there. Sorry, Ms. Spence.
Yes.
Just wanted to tell you that on
Thursday I cannot come to
Okay, no problem.
Yeah, because like I have a medical appointment, so
Okay.
I'll come
Yeah,
every
take a
single
photo
day.
with your doctor. No, I'm kidding. Don't.
And I'll come every single day.
Wow.
I'm
bonus
jo-
mark.
I'm joking. Do not take a picture.
Bonus.
Bonus.
can we do this tomorrow instead of the test?
Oh, this one? Yeah.
Instead of the test. I
Yeah.
mean,
I will get less than.
I was
this
gonna
one.
say you'd probably do worse on this than on
Yeah,
the test because it's a
exactly.
vocab quiz, right? And you need to know the specific words.
and I've not been here for science. lab,
No,
so, I mean,
so you'd be like,
I'm gonna just
oh,
bump this.
you know, yeah.
Question. Wait, did I miss
Create a
any
control
more
group.
review sheets?
Experiment.
Is it
Did
That's
you
like
get the
basic
unit
science.
review?
When do
Energy.
was that
It
like
was. It's the one that we looked at today.
Chemistry is physics and stat.
Okay, hang on.
yeah,
I just need to
I
press
might
stop
recognize-
recording.
Oh yeah.